So the next thing to do would be to actually add those geometry characteristics into our run move function here so that the crawler can actually respond to those characteristics. Now, I think it actually makes sense to adjust the structure of this class a little bit. So we're going to go through this kind of removing, cleaning up, and restructuring this a bit. So we can actually restructure this a bit, and instead of relying always on our connected topology vertices, we will make this so the crawler can move freely in space, but always snap back to the mesh. And then we're going to allow it to make decisions based on not its connected topology vertices, but actually the vertexes at the corner of the face that it is on. So this structure is going to look a little bit different. So instead of getting these connected topology vertexes, we can just get the closest point on the mesh to our current position. So we'll say rs.mesh closest point, and this takes an object ID, a point. So it's going to be a mesh ID, which is our mesh map. So my mesh map.id, and then our current point, so self.pos, and we don't need to specify maximum distance right now. And this is going to return a tuple, including a point, and then an index value of that face. So we actually want to use that index value of the face, and we're going to query that face and see which vertex indices are connected to it. So face index equals, and then we don't want the first value there, which is actually the specific point output. Actually, maybe we want both there. So we're going to take the point and the number, and since this returns a tuple, we don't have to specify the item. Instead, we can just say mesh point, comma, face index, and that way it will separate that tuple output into the actual point on the mesh and then our face index. And now we want to do a similar setup that we've set up here. So right now we're just finding the lowest neighboring vertex, but in this case we want to find the highest curvature value and then maybe highest inclination value as well. And we're going to add all of those up into a vector property, which is then going to be added to our current position and then return back to the closest point on the mesh. So in this case, we don't actually need this self.index, and we don't need it here either. We do need a self.vec, which we can just set equal to 0, 0, 1. And now we need to edit this a bit so that we actually extract each of the vertex indexes from our face. So we can go up to the mesh class and add here self.faces equals rs.faces. So we can feed in here the ID and now use this self.faces. So we want our neighboring vertex indices equal to my mesh map and dot faces of our face index value. And we can just print that to make sure that it's working. We're not calling the faces, we're just feeding in an index value. Okay, and then I'm going to just comment this out for now. Yep, so that's working so far. But actually, this is giving us vertex value outputs. So instead of faces, we actually want our face vertices here. So rs.face vertices. And this is going to output, it says here, containing tuples of 4 numbers that define the vertex indices of each face of the mesh. So this is what we're going to want. And then we can say face vertices. Then feed in the face index still. And now when we hit test, we see that it gives us that tuple of 4 values, which are the index values of the connected to that face. So we can uncomment this section out. We can leave this lowest vertex and lowest index, and then we can just say for n VTX in and VTX indices, and then if my mesh map dot n, not topology vertexes, but just vertexes, again, feed this in. And here too, just change this to vertex, change the index input, and change, actually that is fine. So now if we hit test, let's just double check what we're getting here from NVTX. Yep, so that should be an index value. Here, we don't want to, let's check what we're getting out of this. Not indices. We do actually need to feed in our n_GTX. So this should now work. So we can see that is actually working there. Now, instead of just setting our self.pos to our lowest vertex value, we actually want to add all of this into our self.vec and then say self.pos equals rs.point, and we're going to add our current self.pos to our self.vec, and then we're going to use this same function to snap to the closest point on the mesh. So in this case, we're going to say self.pos equals rs.mesh closest point, our mesh map mesh, and our current position after adding that vector. And we just need the first item in that tuple output there. So this will update our self.pos and append that to our trail points list. So now we just need to define our self.vec. So right now, our self.vec would just equal our desired vertex, so our lowest vertex, minus our self.pos, which would give us the vector from our current position to that vertex. So if we point add, not add point. So now we want to add a few extra things. So we're going to actually average our lowest vertex value, which in this case, we actually don't even need our index here anymore. We want to find our best combination vertex and our best. We can set each of these equal to none. Then we want to say best curvature equals 0, so that 0.0, so that every test will be higher than 0.0 or at least equal to it, and then our best inclination equals 0.0. So this gives us the starting point of our best value being the lowest. And then as we cycle through these vertices, we want to say if mesh map dot, and then we need to grab our topology curvatures, and then we need to convert this vertex index into a topology vertex index. So dot GTXS dot topology index in our GTX. So if that curvature value, and actually not all here, sorry, that's feeding in an index value. So if this is greater than current best, so B underscore C, then B underscore C equals this curvature value. So we're now resetting our best value equal to that current one that was higher, and our best curvature vertex equals this index, but not from our topology curvatures, but our topology vertexes. Now we basically want to just copy this and use the same thing for our inclination. Instead of T curvatures, T inclinations. Instead of B underscore C, it's B underscore I, B underscore I. Change this to inclinations. Best inclination vertex. And now we want our self.vec not to equal lowest vertex minus our current position, but a combination of each of those. So we can say gravity vector, curvature vector, and inclination vector. Say our gravity vector is equal to our lowest vertex minus self.pos. Curvature vector is equal to our best curvature vertex minus self.pos. And our inclination is our best vertex minus self.pos. Now we have 3 output vectors. We just need to average each of those, or we could just add all of them up together. So we can say Vec plus Cvec plus Ivec equals our overall self.vec. Add those to our current position, find the closest point on the mesh to snap to, and set that to our position, and then append to our trails. So now if we hit test, it's giving us an error here. So at 106, that this vertex value it is actually a 0.3f instead of a 0.3d. So in each of these, if we can say rs.course 3D point, then we can get a 3D point instead of a 0.3f. And now this should work. We still want to make sure that our run, let's say it's above 10, and it seems to be getting stuck there because the inclination weighting is too high. So now what we can actually do is, instead of just adding each of these vectors up, we can create weights for each of the vectors and then weight each accordingly. So up at the top here, we're going to actually set new properties. So self.gweight equals 1.0, self.cweight equals 1.0, self.iweight equals 1.0. So we've now set each of these weights. Now we just need to refer to these inside the run function, and we're going to just use these as multipliers to our current vector. So we're going to say rs.vector scale, which takes an input vector and then a scale. So we're going to use self.gweight, then we need our self.cweight to weight our c vector. So rs.vector scale again. Use that c weight as our scale. And then the last one is our inclination. rs.vector scale. And put that inclination vector and our inclination weight. So now we're scaling all of these together. If we wanted to weight gravity more or entirely, we can just turn these other two to 0 and hit test. We may need to turn up the weight of gravity in this case so that it actually flows downward, which you can see is happening. So if we set this value to 4, we can see that now our crawlers are actually even jumping off the mesh. They're actually still snapping, but the interpolated curve is coming off the mesh because that value is so high. If we turn this down to 3, for these cases, we're actually getting an error because it's not overriding this inclination value. So just to make sure this doesn't happen, we can set an error trap here. So if best underscore inclination not equal to none, then we'll set that. And then we'll say else ivec equals 0, 0, 0. And we can do that check for each of these. So if best curvature vertex not equal to none, else cvec equals 0, 0, 0. So this will just give us a check in case we get a none value like that. So then if we hit test, we can see it running based on gravity. So it's following the kind of points down the mesh based on a kind of gravitational flow. Now, if we were to turn our curvature weighting up, it should start to snap more to high curvature values on the way down, which you can see it's kind of starting to do. If we turn our gravity down so that those are even, so now it's actually getting stuck because the curvature value is too high. So we probably always want our gravitational flow to be slightly higher than our curvature weighting. Maybe we could try curvature at 0.4, gravity at 2, and maybe inclination at 0.2. Okay, and now if we just hit OK, we can actually go through and set more points here. So we can right click, set multiple points. And now we have all of those points flowing on our surface. And the last thing for this tutorial is going to be if we want to give a check for our mesh area coverage. So we can see certain trails, like let's say here, there's no other neighboring trails near it. In other places, it gets a bit denser, so down here. So if we wanted to do a check for how many items are within a certain distance of us, and if they're within a certain distance or a certain number are within a certain distance, we wanted to maybe do nothing, but if there are too few around us, we want to increase our coverage and branch. One way to do this is to actually have a get neighbors function. So if I just hit enter here, we can say def.get neighbors. And now we're going to need a few extra properties up at the top here. So we need our self.neighbors list, which we can set equal to a blank list to start. And then we need self.radius, which is that distance to search. For now, we can say 1000. And then we can just clear our self.neighbors list, because if we were to call this without clearing it, we might just append to the existing list of neighbors. So we want to make sure it's cleared every time it's called. And what we're going to use here is a tree search algorithm. So right now we're actually building our tree using rhino.geometry.rtree. And then we want to cycle through each item in our population. So our population at the top here. So this is actually lowercase population. So for each item with each index in population, which is our population of our class, insert each of those items with that given index into our tree. Now we're going to say instantiate a rhino.geometry.sphere at our current position with our specified radius, so 1000, to create a search sphere. And then we're going to call a tree callback. And this argument basically says to append to the list self.neighbors whatever the return IDs are from this search algorithm. So now we're running the actual search down here using the search sphere as an input and the callback. So whatever values it returns, it will append to that list of neighbors. Now, if we actually just call this function, so self.getCallback, we're going to do this after our trail points here. So self.getNeighbors. And then we want to say if length self.neighbors is less than a certain value, so let's say 4, then we want to instantiate a new set of instances of this class. So this is going to be similar to a kind of branching setup. So if we don't have enough neighbors near us, then we want to create our own neighbors essentially in our vicinity. And in this case, we're going to say for and vertex in, and then we're just going to use our list of vertex indices here. And we're going to instantiate new crawlers, which takes our point input. So instantiate, so create a new object of class crawler and feed in not our self.pos, which is our current position, but instead the position of our vertex. So this is just the index. We actually need self.vertexes, or actually we need my mesh map.vertexes of n_vertex. And just to be safe, we can coerce this into a 3D point. And now we can't just leave it there. This is going to add new instantiations, but we need to do what we're doing here in looping through our original crawlers and append this crawler to our population. So we need to add population.append and append these new instances of crawler to our population. So now we should be able to hit test. So now we have our branching mesh crawlers, which flow along the surface of the mesh. That's all for the mesh crawler tutorial. Try to go through and play with the kind of weights, maybe change the geometric properties that you're using for the evaluation. In this case, you can see that the crawlers are behaving, are creating a kind of chaotic or messy ordering. So find ways of maybe discretizing the vector motion so it's a bit cleaner here, or constraining it in a specific way. Maybe you can try and use an acceleration property to actually create momentum in this instead of adding a velocity to the current position. There are a lot of ways that you can edit this type of structure. So spend some time trying to do that to get it to actually perform how you would like it to perform. But you should be able to get these to start to branch out for kind of maximum coverage of the mesh geometry, while also still favoring particular areas of curvature or continuing to move forward. So you could have a kind of bias programmed into this that it always wants to move forward a certain amount. This would be similar to using a kind of acceleration property along with the velocity and position property. In the next tutorial, we're going over an introduction to Visos as well as its installation, and we'll be able to look at how to feed this trail information into the Visos robotic simulation so that we can actually get the robot end effector to trace out these trails on this mesh.